ChatGPT confidently told someone their flight was delayed, except that flight did not exist. The model hallucinated an entire airline schedule because it had no access to real data. Now imagine the same AI, but instead of making things up, it searches through your actual documents, finds the relevant information, and answers based on facts. That is RAG, Retrieval Augmented Generation. And it is the single most important architecture pattern in production AI today. By the end of this video, you will understand exactly how it works and why every serious AI team is using it. Large language models have a dirty secret. They cannot tell the difference between what they know and what they are making up. When you ask GPT about your company's leave policy or last quarter's sales numbers, it has two choices: admit ignorance or confidently fabricate an answer. Guess which one it picks more often? This is not a bug. It is how these models fundamentally work. They are trained to predict plausible next tokens, not to verify truth. Here is the core issue. LLMs store everything they learned during training inside their parameters. Billions of neural network weights. This is called parametric knowledge. It is frozen at training time and expensive to update. But real-world information changes constantly. Your inventory updates hourly. Legal regulations shift quarterly. This is non-parametric knowledge, external, dynamic, specific to your context. RAG bridges these two worlds. RAG works in 3 stages. First, you take your documents and convert them into searchable vectors. We call this the indexing phase. Second, when a user asks a question, you search those vectors to find relevant chunks. The retrieval phase. Third, you combine those chunks with the original question and feed everything to the LLM. The generation phase. The model now answers based on actual context, not just its training data. Simple concept, powerful results. You might ask, why not just fine-tune the model on your data? 3 reasons. First, fine-tuning is expensive and slow. You need significant compute and expertise. Second, fine-tuning does not add factual knowledge reliably. Models learn patterns, not facts. Third, and most critically, fine-tuning cannot handle information that changes. Your product catalog updates daily. RAG handles this naturally because retrieval happens at query time, not training time. Before you can search documents, you need to break them into pieces. This is chunking, and it is deceptively important. Chunk too large and you dilute the relevant information with noise. Chunk too small and you lose context. A single sentence about the quarterly results means nothing without knowing which quarter and which company. Most teams start with chunks of 500 to 1000 tokens, with some overlap between adjacent chunks to preserve context at boundaries. Fixed size chunking is just the beginning. Semantic chunking splits at natural topic boundaries, using an embedding model to detect when the subject changes. Recursive chunking tries paragraphs first, then sentences, then characters, respecting document structure. For code, you chunk by functions or classes. For legal documents, by clauses. The right strategy depends entirely on your content type. There is no universal answer here. Now we need to make these chunks searchable. Enter embeddings, numerical representations of meaning. An embedding model reads your text and outputs a vector, typically 768 to 1536 numbers. Here is the magic. Texts with similar meanings end up close together in this vector space. The words dog and puppy have similar embeddings. So do machine learning and ML algorithms. This is how we enable semantic search, finding content by meaning, not just keyword matching. Not all embedding models are equal. OpenAI's text embedding HE3 models are popular and capable. Cohere's embed models excel at multilingual content. Open source options like BGE and E5 from Hugging Face offer strong performance without API costs. The MTEB leaderboard benchmarks these models across tasks: retrieval, classification, clustering. For most RAG applications, you want a model optimized specifically for retrieval, not general purpose embeddings. You have millions of chunk embeddings. Where do you store them? Regular databases are terrible at finding similar vectors. They would need to compare your query against every single stored vector. Vector databases solve this with specialized index structures that enable approximate nearest neighbor search. Think of it like a library catalog system. Instead of scanning every book, you navigate to the right section first. Pinecone, Weaviate, Milvus, Qdirant, and Chroma are the major players here. Most vector databases use an algorithm called ANSW, Hierarchical Navigable Small World Graphs. Picture a social network with layers. The top layer has few well-connected hub nodes, celebrities if you will. Lower layers are denser with regular connections. To find similar vectors, you start at a hub, greedily walk toward your target, then drop down a layer and repeat. This hierarchical structure lets you skip most of the database while still finding excellent matches. Approximate? Yes, but blazingly fast. How do we measure if two vectors are similar? The most common metric is cosine similarity. It measures the angle between two vectors, ignoring their magnitude. Vectors pointing the same direction have similarity of 1. Perpendicular vectors score 0. Opposite directions score negative 1. Why cosine over Euclidean distance? Because we care about semantic direction, not scale. A longer document should not be considered different just because its embedding has larger values. When a user asks a question, the retrieval pipeline activates. First, you embed their query using the same model you used for documents. This is critical for consistency. Then you search your vector database for the top k most similar chunks, typically 3 to 10 depending on your context window. Each result comes with a similarity score. Higher scores mean better semantic matches. You have just turned a natural language question into a database lookup that understands meaning. Retrieved chunks alone are not useful. You need to present them to the LLM effectively. This is where RAG-specific prompt engineering comes in. Your prompt should clearly separate the retrieved context from the question. Instruct the model to answer only using the provided context. Add a fallback instruction. If the context does not contain the answer, say so instead of guessing. This simple structure dramatically reduces hallucinations compared to naive approaches. LLMs have limited context windows. GPT-4 Turbo handles 128k tokens, Claude 3 goes up to 200k. Sounds huge, but it fills quickly. Your system prompt, retrieve chunks, conversation history, and the question itself all compete for space. Retrieving too many chunks wastes context and increases cost. Too few, and you miss relevant information. Production systems dynamically adjust retrieval based on available context budget, prioritizing the most relevant chunks. Pure semantic search has a weakness. It can miss exact keyword matches that matter. If someone searches for error code null ref 5032, semantic similarity might return general null reference content instead of that specific error. Hybrid search combines vector similarity with traditional keyword search like BM25. You run both searches, then merge results using reciprocal rank fusion. This catches both conceptual matches and precise term matches. Most production RAG systems use hybrid search. Initial retrieval prioritizes speed. You are searching millions of vectors, but fast does not always mean accurate. Re-ranking adds a second pass using a more sophisticated model. Cross-encoders like Cohere Re-Rank, or BGE Re-Ranker see the query and each candidate together, understanding the relationship more deeply than embedding comparison alone. This is computationally expensive, so you only re-rank the top 20 to 50 initial results. The quality improvement is often dramatic. How do you know if your RAG system is working? You need separate metrics for retrieval and generation. For retrieval, measure recall at K. Did the relevant documents appear in your top K results? Mean reciprocal rank rewards finding relevant docs earlier. For generation, check faithfulness. Does the answer actually reflect the retrieved context? Answer relevance measures if the response addresses the question. Tools like Ragas and Langsmith help automate this evaluation. Even well-built RAG systems fail in predictable ways. Retrieval failure happens when relevant documents exist but are not found, often due to vocabulary mismatch between query and content. Context poisoning occurs when irrelevant but high similarity chunks mislead the model. Lost in the middle is a known LLM bias, where models ignore information in the middle of long contexts, favoring the beginning and end. Understanding these failure modes helps you debug and improve your system. User queries are often terrible for retrieval. They are vague, use different terminology than your documents, or ask multiple questions at once. Query transformation fixes this. Use an LLM to rewrite the query into better search terms, expand it with synonyms, or decompose complex questions into simpler subqueries. HyDE, hypothetical document embedding, is particularly clever. You ask the LLM to imagine what a perfect answer document would look like, then search for similar real documents. In production, RAG systems get complex. You need an ingestion pipeline that monitors source documents for changes and reindexes automatically. Caching layers avoid redundant embedding computations. Rate limiting protects your API budgets. Observability tools track latency, retrieval quality, and cost per query. Multi-tenant systems partition vector databases by customer. Streaming responses improve perceived latency. The simple three-stage diagram we started with grows into a full microservices architecture. RAG is evolving rapidly. Multimodal RAG retrieves images and videos alongside text. Agentic RAG systems decide dynamically whether to retrieve, when to retrieve, and from which sources. Graph RAG combines vector search with knowledge graphs for better reasoning about relationships. Self-reflective RAG evaluates its own answers and retrieves additional context when uncertain. The core principle remains: ground generation in retrieved facts. But the implementations grow more sophisticated every month. Let us lock in what you learned today. First, RAG solves the hallucination problem by grounding LLM responses in retrieved facts, rather than relying solely on parametric knowledge. Second, the core pipeline is index, retrieve, generate, with embeddings and vector databases enabling semantic search at scale. Third, production systems layer on hybrid search, re-ranking, and query transformation to dramatically improve quality. This is the foundation of almost every enterprise AI application being built right now. Next up, watch our video on building a RAG system from scratch with LangChain, where we turn this theory into working code. If this breakdown helped you understand RAG, smash that subscribe button and hit the bell so you never miss a video. Drop a comment below. What are you planning to build with RAG? I genuinely want to know.